Humans consider themselves unique, so they have rooted their whole theory of existence on their uniqueness. One is their unit of measure, but it's not. Every social structure we build is only a mere sketch. We have codified our existence to bring it down to human size, to make it comprehensible. To help us forget its unfathomable scale, we created a scale. But if the universe is not regulated by mathematical laws, and humans are not the unit of measurement, then what governs on that? Time gives legitimacy to its existence. Time is the only true unit of measure. It provides evidence for matter's existence. Without time, we don't exist. Time is unity. Think of a river. The river moves with a smooth, steady rhythm, its waters gliding over rocks and swirling into eddies. From afar, the river might seem like a single, continuous flow, a ribbon of water stretching from the heights of the mountain to the valleys below. But stand at the edge and watch it long enough, and you'll notice the river is never the same. The water you see now is not the same water you saw a moment ago. Heraclitus once said, "You cannot step into the same river twice. Each drop, once it passes, is gone forever, replaced by new ones, which in turn will also rush by and disappear downstream." And yet, despite this endless change, the river seems eternal. It's always there, flowing onward, never pausing, never retreating. This river, always moving forward, is much like how we imagine something else. Time. We often picture time as a flowing current, sweeping us along in its relentless stream, from past to future. Like the river, we cannot step into the same moment twice. Every instant is new, different, slipping away as quickly as it arrives. Yet just as the river bends or slows, so too can time. Einstein showed us that time can stretch and contract depending on where you are and how fast you're moving. Imagine speeding down a river at breakneck pace. Everything around you blurs, while to someone sitting still on the bank, the flow seems slower, almost calm. Time behaves in a similar way. For someone moving near the speed of light, time slows down compared to someone standing still. And there's more. Picture a river that freezes. When the flow stops, the water is trapped in a single moment, creating a crystalline surface that glistens in the sunlight. In certain extreme conditions, time itself pauses, much like the still surface of an icy river. The water beneath remains suspended, caught in a moment of stillness. In the depths of space, near a black hole, time slows to almost a standstill. The river of time, which we believe moves ever forward, becomes sluggish and nearly frozen, ensnared by the gravity of the cosmos. We live our lives feeling time rush past us like the river. But if we look closer, we begin to see that time isn't as straightforward as we might think. The river's flow can be bent, stopped, or stretched in ways that seem impossible at first glance. Is time any different? Could it be that time is, in fact, just an illusion? The arrow of time points in one direction, from the past to the future, marking a clear distinction between what has already happened and what is yet to come. This forward flow is evident in everything around us. Waves crash and recede, leaves fall and decay, and energy dissipates as processes unfold in irreversible ways. But why does time only seem to move in one way? And is this movement a fundamental property of the universe or just an illusion of human perception? One of the key to these questions lie in something that, at first glance, appears unrelated, something hidden in the fabric of reality itself. It was the dawn of the Industrial Revolution. Steam engines were driving trains across continents, powering factories and transforming society. But despite the practical mastery of these engines, there was still a fundamental mystery at play. What exactly was happening inside these machines, and why did they seem to waste so much energy? Why couldn't they run forever? Rudolf Clausius was a curious man, and these questions stuck with him. Heat, he knew, wasn't a substance. It wasn't some invisible fluid that moved between objects, as scientists once believed. It was energy in motion, transferred from one system to another. But something about this energy puzzled him. When steam engines burned fuel to create motion, a lot of heat seemed to disappear into the environment, wasted and unusable. Why, Clausius wondered, did energy seem to flow in only one direction, from hot to cold, from useful to useless? And more importantly, why couldn't you reverse the process to recover the lost energy? What was this invisible barrier that made some transformations possible and others impossible? Clausius's moment of insight came when he began to see heat not as a magical, flowing entity, but as energy that obeyed strict rules, rules that couldn't be broken no matter how cleverly you built your engine. After years of experiments, calculations, and thought, he formulated a principle that would forever change our understanding of the universe, the second law of thermodynamics. And it states, in any closed system, the total entropy will always increase over time. Energy will always spread out and become more disordered, making some processes irreversible. Imagine a steam engine with two chambers, one filled with hot steam, the other cooler. As the steam flows from the hot side to the cold side, it pushes a piston, converting some of the heat energy into mechanical work, like moving a wheel. But here's the catch. Not all the energy from the steam is converted into useful work. Some of it leaks out as waste heat, spreading into the environment. No matter how well you design the engine, you can't stop this leakage. Heat always flows from the hot side to the cold side, never the other way around. This flow is what Clausius realized was the heart of the second law. In nature, energy spreads out. Hot things cool down. Order becomes disorder. This tendency toward disorder, this relentless march toward randomness, is what Clausius named entropy. And once entropy increases, it's nearly impossible to reverse it. Let's take a simple example. Picture a box filled with 100 marbles. At first, you arrange all the red marbles on one side and all the blue marbles on the other. This is a state of low entropy, highly ordered and organized. Now shake the box. The marbles will scatter randomly, mixing together. After a few shakes, you'll see a chaotic jumble of colors. This mixed state is high entropy. The marbles are no longer arranged neatly, and it would take considerable time and effort to separate them again. Now shake the box continuously. What are the chances that by sheer luck, all the red marbles will spontaneously regroup on one side? Essentially, zero. That's the essence of entropy. Once a system becomes disordered, the odds of it returning to a highly ordered state are so small that it's effectively impossible. Energy, like those marbles, naturally spreads out. In thermodynamics, it means heat spreads from hot areas to cold ones, and it never flows backward on its own. You could build the most advanced machine imaginable, and still, it would never extract energy from cold steam to heat it up again. Entropy would always have the final word. Clausius's law didn't just explain the workings of engines, it had profound implications for time itself. The second law of thermodynamics suggests that the direction of time is tied to the increase of entropy. The reason we experience time as moving forward rather than backward is that entropy is always increasing. You remember the past, the time when the marbles were neatly separated because it was a state of lower entropy. But you don't remember the future, because that's where the marbles are mixed, the steam has cooled, and the energy has spread out. Consider your morning coffee. When you pour it, the steam rises, and the coffee quickly cools. The heat energy from the coffee spreads into the surrounding air, increasing the entropy of the system. It's impossible to undo this process. You'll never see the steam gather back into the coffee to make it hot again. In fact, the only way to reheat the coffee is to add new energy, perhaps by placing it in a microwave. This, too, increases the overall entropy of the system because the microwave uses electricity, which itself generates waste heat. Every time we do work or transfer energy, entropy increases somewhere in the universe. Or think of an egg. Before it's cracked, the egg is a highly ordered system. Its yolk and whites are neatly contained within a shell. But the moment you crack it open, the egg's entropy increases. The whites and yolk mix together, and as you cook it, heat spreads through the liquid, changing its structure. You'll never get the egg back into its original low-entropy state. You'd have to manipulate each molecule with impossibly fine precision, putting every drop of yolk back into the exact place it was before. The increase in entropy makes the transformation irreversible, and it's that irreversibility that gives time its forward arrow. Entropy ensures that time always moves forward, from unburned match to ashes, from whole egg to breakfast. It's what gives our experience of time a kind of arrow, always pointing in the same direction. But for most of human history, people didn't think of time in terms of entropy or physics. They thought of it in terms of cycles, sunrise and sunset, the changing seasons, the phases of the moon. In ancient times, people's relationship with time was inseparable from the natural world. Before clocks ticked off the minutes and smartphones buzzed with reminders, the movements of the sky, the phases of the moon, and the turning of the seasons were the only clocks people knew. The cycles of nature not only told people when to plant, harvest, or celebrate, but also gave rise to some of the earliest calendars, tools that shaped our weeks, months, and years in ways that still influence us today. In ancient Egypt, the rhythm of life was set by the flooding of the Nile River. Each year, the river swelled with waters from distant rains, spilling over its banks and transforming parched fields into fertile land. To the Egyptians, this wasn't just an annual inconvenience, it was a divine event, both destructive and life-giving. The flood marked the beginning of a new agricultural cycle, a natural reset button that dictated when to sow seeds and reap harvests. Egyptian priests closely monitored the sky for signs of the star Sirius, whose rising in the dawn sky coincided with the floods. Over time, this observation became the backbone of the Egyptian solar calendar. A 365-day year divided into 3 seasons: Akhet, the flood; Peret, the planting season; and Shemu, the dry harvest season. But tracking entire years was not enough. People needed to measure the hours of the day, too. The Egyptians pioneered sundials, carving stone markers to follow the movement of shadows as the sun arced across the sky. Early sundials weren't precise by modern standards. They divided the day into broad segments, offering more of a general sense of morning, midday, and evening. Life at that time didn't need the precision of modern schedules. It was enough to know when it was time to tend the fields or return home before dark. Time was measured in rhythms, not in minutes, and the ebb and flow of daily life mirrored the slower pulse of the natural world. The Egyptians also developed water clocks, or clepsydra. These were vessels with a tiny hole near the bottom that allowed water to drip out slowly, marking the passage of time. As the water level dropped, it revealed different markings that indicated how much time had passed. Water clocks were used in temples to track ritual activities at night when the sun, and therefore the sundial, was no longer of use. Time to them was a sacred thing, tied to their ceremonies, prayers, and the great rhythm of life and death governed by the gods. Over time, measuring tools became more refined, but their purpose remained the same: to align human life with the patterns of nature. For most of history, time wasn't rigid. It was flexible, responding to the cycles of light and dark, the seasons of growth and rest. Farmers rose with the sun and slept when it set. In this world, time was a guide, not a tyrant, helping people navigate life's uncertainties, but never dictating every second. The shift from natural time to mechanical time began quietly, like the first few ticks of a clock, barely noticed by the world it would soon reshape. It all started in the late 13th century when the first mechanical clocks were installed in European church towers. These early clocks were crude by today's standards. Instead of hands moving across a dial, they used bells to mark the hours, ringing out across villages to call monks to prayer or signal townspeople to gather for markets. Time, which had once been personal and local, was becoming something public, something heard, not just felt. But even at this stage, time still served the rhythms of daily life. The bells didn't demand obedience, they simply announced the passing of hours. The real shift came in the 17th century with Christian Huygens, a Dutch scientist whose restless mind turned a casual observation into one of the most transformative inventions of all time: the pendulum clock. Huygens was fascinated by the precise movement of the heavens, the way planets swung around the sun, the moon circled the earth, and the stars returned to the same points in the sky, night after night. Nature, Huygens believed, operated on a grand mechanical rhythm, one that could be understood and measured. But the timekeeping devices of his era, sundials and water clocks, were crude and prone to drift. Time slipped through their cracks. What if, Huygens thought, it was possible to create a clock that never faltered, a machine that ticked as reliably as the cosmos moved? Huygens' breakthrough came from a curious observation about pendulums. A swinging pendulum, he noticed, followed a steady and predictable rhythm. It always took the same amount of time to swing back and forth, regardless of the size of the arc. This was a property now known as isochronism, and it intrigued him. If this natural regularity could be harnessed, Huygens realized, it could serve as the engine of a new kind of clock, one far more accurate than anything the world had seen before. In 1656, Huygens built the first pendulum clock, capable of measuring time with an accuracy of within 10 seconds per day, a vast improvement over anything available at the time. Around the same time as Huygens' pendulum clock revolutionized the measurement of time, another figure was also working on ideas that would forever reshape our understanding of the world: Isaac Newton. Both Huygens and Newton lived in the 17th century, an era of scientific transformation. While Huygens was perfecting the mechanics of pendulums and timekeeping, Newton was developing a framework that would define how we think about time and space for centuries: classical mechanics. Newton's laws of motion, laid out in his seminal work, often just called the Principia, described a universe that operated like a perfectly engineered machine. In this view, time flowed uniformly and independently, unaffected by anything happening in the world. Newton wrote, "Absolute, true and mathematical time of itself and from its own nature flows equably without relation to anything external." In other words, time in Newton's universe was like the steady tick of a pendulum, constant, unwavering, and eternal. It marched forward regardless of the events unfolding within it. To understand Newton's concept of time, think of it like a cosmic stage where events unfold. The stage is unchanging, and the actors, the planets, stars, and every object on Earth move according to well-defined rules. These rules are Newton's laws of motion, which describe how forces cause objects to move. The beauty of these laws is their simplicity and precision. Just as Huygens' pendulum clock made time measurable in seconds and minutes, Newton's equations made it possible to predict the motion of objects with almost frightening accuracy. A cannonball fired into the air, a planet orbiting the sun, or even an apple falling from a tree, all could be described using the same basic principles. In this Newtonian universe, time was absolute, and space was an empty, three-dimensional grid in which objects existed and moved. An easy way to visualize this is to draw a graph with three axes: length, width, and height. This grid represents space, and every object in the universe occupies a specific point on it. Now, time is a separate, invisible line that stretches forward into the future. The objects in space move along this time axis, but time itself doesn't bend or change. It simply advances, second by second, like the steady tick of Huygens' pendulum. Newton's laws made it possible to predict how objects would move through this grid of space and time. For example, if you were to throw a ball into the air, Newton's second law, where force equals mass times acceleration, would allow you to calculate exactly how high the ball would go and when it would return to the ground. Time played a crucial role in these calculations, acting as the invisible framework that held the entire system together. But crucially, time itself wasn't affected by the ball's motion. It ticked forward evenly, just as it would if the ball had never been thrown at all. Newton's view of time as an unchanging universal backdrop was so compelling that it shaped the scientific world for centuries. His laws governed everything from the swing of Huygens' pendulum to the trajectory of planets, creating a vision of a clockwork universe where time flowed like a river, steady and predictable. Huygens' pendulum, ticking in perfect harmony with Newton's equations, seemed to capture the very essence of time's regularity. In this world, every second was identical to the last, and every event could be traced back to precise causes. And Clausius's work on entropy introduced a new dimension to the flow of time. Clausius's second law of thermodynamics revealed that while Newton's equations might predict the motion of objects and time, they said nothing about the direction of time. Clausius's entropy law pointed to an irreversible arrow of time, where systems naturally moved from order to disorder, never the other way around. Time wasn't just a passive river anymore. It had a direction, a purpose, an inevitable march towards the future. And so, the universe began to seem less like eternal clock and more like a one-way street, with entropy as its guiding force. The steady rhythm of Huygens' pendulum was still there, but now something else was at play, a cosmic trend towards chaos that Newton's tidy equations could not explain. But what if this arrow of time isn't as straightforward as it seems? What if everything we think we know about time, about its flow, its direction, could be overturned? Albert Einstein was a dreamer long before he was a scientist. Growing up in the small German town of Ulm, The young Einstein was known more for his daydreaming than for his academic prowess. He found the rigid schooling systems of his youth stifling, far more interested in the mysteries of the universe than in rote memorization or mechanical obedience. But there was one thing that captured his imagination like nothing else: time. It seemed to young Einstein that time was something more mysterious than a clock ticking in the corner of the room. What, he wondered, if time wasn't as constant as it appeared? What if time could bend? Einstein's early curiosity about time was ignited by a thought experiment that would forever change the course of physics. He began to realize that time might not be the fixed entity everyone assumed it to be. What if time, like space, could be affected by motion? What if time itself could bend? In 1905, as a young clerk in a Swiss patent office, his thought experiments finally crystallized into what we now know as the special theory of relativity. In this theory, Einstein proposed something revolutionary. Time and space were not separate entities, but part of a single fabric, woven together into what he called space-time. The motion of objects through space, he argued, could actually affect the passage of time. The faster you moved through space, the slower time passed for you. It was a startling conclusion, one that flew in the face of centuries of classical physics, where Newton said that space and time act separately. In a future not too distant from us, there were two identical twins, Alice and Bob. They were born on the same day, at the same time, and lived their entire childhood together, always the same age. But one day, Alice, ever the adventurer, decided to set off on a journey to the stars. Alice boards a spaceship capable of incredible speeds, close to the speed of light. Bob, on the other hand, stays back on Earth, watching his sister take off into the vast unknown. Now here's where things get interesting. According to Einstein's theory of special relativity, time behaves differently for Alice, the one speeding through space, than it does for Bob, who remains stationary on Earth. The faster Alice travels, the slower time ticks for her, compared to Bob. Alice's journey takes her to a distant star system many light years away. Let's say it's a round trip. She speeds out into the cosmos, reaches a far-off star, and then turns around to head back to Earth. From Alice's point of view, the trip seems relatively short. After all, her clock isn't ticking as fast as Bob's. But Bob, watching from Earth, experiences a very different reality. Finally, Alice returns to Earth. The moment of truth arrives. Bob runs out to greet his sister, but there's a shocking difference. Bob is now much older than Alice. While only a few years may have passed for Alice on her high-speed journey, Bob has aged far more during her absence. How could this be? This is the heart of the twin paradox. Two twins, born at the same time, but due to one traveling near the speed of light, they no longer age at the same rate. The faster Alice traveled, the slower time passed for her relative to Bob. And when they reunite, the difference is undeniable. Time has bent and stretched. The twin paradox isn't just a hypothetical thought experiment, it's been tested, and the results consistently support Einstein's predictions. In 1971, the world witnessed an experiment that seemed straight out of science fiction. The Haffel-Keating experiment, as it would come to be known, was a direct test of one of the strangest consequences of Einstein's theory of relativity: gravitational time dilation. Joseph Haffel, a physicist, and Richard Keating, an astronomer, were determined to test whether gravitational time dilation and the relativistic effects of motion, what's called kinematic time dilation, could be observed using modern technology. By the late 1960s and early 1970s, atomic clocks had become precise enough to measure tiny differences in time, down to nanoseconds. This development, paired with the relatively high speeds of commercial jetliners and the ability to fly at high altitudes, opened the door for a truly novel experiment. The duo theorized that by flying atomic clocks around the world, they could observe the twin paradox in action, even if on a much smaller scale. The idea was simple. Planes fly at high altitudes, where Earth's gravitational pull is weaker, and they move at high speeds relative to the ground. Both of these conditions should cause time on the planes to tick differently from time on the ground. In effect, they wanted to replicate the twin paradox with highly sensitive clocks as their stand-ins for the traveling twin and the twin on Earth. The real challenge lay in the details, coordinating flights, ensuring precision in their measurements, and accounting for countless variables. In October 1971, Hafele and Keating boarded 2 commercial airliners with 4 cesium-beam atomic clocks. These tiny differences were enough to demonstrate that time really does behave differently depending on speed and gravity. The implications of Hafele and Keating's experiment was beyond what we imagined. It was the foundation for technologies that would soon become central to modern life. Today, systems like GPS rely on an understanding of both general and special relativity to function. Satellites orbiting Earth must account for the fact that their clocks, far from the gravitational pull of the planet and moving at high speeds, tick faster than those on the ground. Without these corrections, GPS systems would quickly become inaccurate, leading to navigation errors of miles in just a day. GPS satellites orbit the Earth at an altitude of about 20,200 kilometers and move at speeds of roughly 14,000 kilometers per hour. Each satellite carries an extremely accurate atomic clock, just like the ones used in the Hafele-Keating experiment. These clocks are synchronized with clocks on the ground, but as Einstein predicted, they don't stay synchronized for long. First, because the satellites are moving quickly relative to the Earth's surface, special relativity comes into play, slowing down time for them compared to an observer on the ground. This is kinematic time dilation. But the satellites are also far from the gravitational pull of Earth, so according to general relativity, time ticks faster for them than it does for clocks on Earth. The combined effect of these 2 forms of time dilation is critical for the accuracy of GPS. Special relativity predicts that the satellite clocks should tick about 7 microseconds, 7 millionths of a second, slower each day compared to Earthbound clocks. Meanwhile, general relativity predicts that because the satellites are farther from the Earth's gravity, their clocks should run about 45 microseconds faster per day. The net effect is that time on the GPS satellites ticks about 38 microseconds faster per day than clocks on the ground. While 38 microseconds may seem like a tiny difference, GPS depends on the synchronization of time to calculate position. The system works by triangulating signals from multiple satellites, calculating how long it takes for a signal to reach a receiver from different satellites. If the satellite clocks were even slightly off, this timing error would cascade into navigational errors. In fact, without accounting for these relativistic effects, GPS systems would accumulate errors of around 10 kilometers, about 6 miles per day. Thus, to ensure the accuracy of GPS, the system engineers apply precise corrections to compensate for time dilation. Every GPS satellite has a system that adjusts its clocks to account for both the speed of the satellite and the weaker gravitational field at high altitude. But as engineers have learned to adjust for time dilation for GPS, a new challenge has emerged in keeping time. You see, the Earth's rotation is not perfectly steady. It slows down over time due to tidal forces and other factors. Our standard measurement of time, however, based on atomic clocks, is extremely steady. Over months and years, the slight variations in Earth's rotation accumulate, causing atomic time and Earth's rotational time to drift out of sync. To bridge this growing gap, scientists introduce a leap second. This extra second is added to Coordinated Universal Time, UTC, to keep it in line with the solar time, usually at the end of June or December. And here's where the problems begin. Most computers and servers worldwide run on a system of continuous, ever-forward counting time. They don't expect a second to repeat or disappear. When a leap second is added, clocks on computers must account for a rare and irregular second. Unfortunately, this tiny hiccup can trigger major malfunctions in software systems, leading to crashes, freezes, or even more dangerous consequences. One of the most infamous cases occurred in 2012 when a leap second was added on June 30th. Major websites and online services, including Reddit, Mozilla, and LinkedIn, experienced significant outages. The root cause: these systems weren't programmed to handle the leap second correctly. Most servers rely on the Network Time Protocol, NTP, to keep their clocks in sync. When NTP informed them that an extra second had been inserted, many systems tried to process this additional second, but the software wasn't prepared to handle the irregularity, leading to crashes and timeouts. Time is critical in these industries, where every second or even millisecond can make a difference in trades and transactions. When the leap second disrupted the normal flow of time, financial systems had to scramble to compensate. Engineers have developed creative solutions to minimize the impact of leap seconds. One such solution is called leap smearing, which was introduced by companies like Google. Instead of adding a leap second all at once, Google's servers gradually spread the leap second over a 24-hour period by slightly lengthening each second leading up to the event. This process smooths the transition and prevents the disruptions caused by the sudden addition of an extra second. But what if, instead of merely adjusting seconds, we could stop them altogether? What if, for a brief moment, time itself could be frozen, not just in theory, but in practice? There are whispers in the scientific community, hidden within the equations of quantum mechanics, of phenomena that could stretch the boundaries of time beyond recognition. And perhaps, just perhaps, we're closer to uncovering the first real glimpse of this elusive, chilling concept than anyone is prepared to admit. In the spring of 1963, a young Kip Thorne, fresh from a PhD program at Princeton, stood in awe as he visited John Archibald Wheeler's office. Wheeler, one of the great theoretical physicists of the 20th century, was famous for pushing the boundaries of human understanding, from quantum mechanics to general relativity. Thorne's first encounter with the concept of black holes began in that office, a conversation that would change the course of his life. Wheeler spoke about the then controversial idea that massive stars could collapse into infinitely dense points, regions where gravity would overpower all other forces and distort the very fabric of space-time. Wheeler called them black holes. At that moment, Thorne became hooked. From that day, the young physicist dedicated himself to uncovering the relationship between black holes, gravity, and time. Over the next few decades, Kip Thorne became one of the leading voices in the study of general relativity, focusing particularly on how extreme gravitational phenomena influence time. His career was built on the idea that black holes were not only real, but that they held the key to unlocking profound truths about the nature of time itself. Thorne realized early on that Einstein's theory of general relativity predicted something extraordinary. The closer you get to a massive gravitational field, like the edge of a black hole, the more time stretches and distorts. For Thorne, understanding this time dilation was not just about equations, it was about answering a haunting question: could time ever stop? And if so, what would that mean? In technical terms, the relationship between time and gravity can be traced to Einstein's field equations, which describe how mass and energy warp space-time. At the heart of this theory lies the concept of space-time curvature, the idea that massive objects bend the geometry of the universe. The stronger the gravitational field, the more pronounced this curvature, and the slower time flows in that region. This effect, known as gravitational time dilation, has been confirmed through experiments on Earth, such as with precise atomic clocks flown on airplanes. But it reaches its extreme near black holes. Alice wasn't content with just one journey into the mysteries of time. After her light-speed adventure, where she had witnessed the effects of relativity firsthand, there was something deeper she needed to explore: the nature of time near a black hole, where gravity twisted it to its breaking point. Her new mission was set in the Sagittarius A system, the supermassive black hole lurking at the center of the Milky Way galaxy. The black hole, a monstrous entity with a mass millions of times that of the Sun, was the perfect place to push the limits of everything she and Bob had learned. The journey from Andromeda to Sagittarius A took weeks, but to Alice in her light-speed spacecraft, it passed in a blur. The vast distances between stars felt inconsequential as she hurtled through space, propelled by the ship's advanced fusion drive. Her ship flew past distant star clusters and through regions of space rarely visited by humans, heading for the galactic core. As the ship gets closer to the black hole, the dense region surrounding Sagittarius A, known as the accretion disk, glowed with radiation from matter swirling around the black hole at incredible speeds. But beyond that disk, there was only darkness, a void where light itself couldn't escape. As Alice's spacecraft drifted ever closer to the event horizon of Sagittarius A, the effects of gravitational time dilation became more and more pronounced. The massive black hole, with its immense gravitational pull, was bending space-time so severely that it was no longer just a theoretical concept on paper. The deeper she ventured into the black hole's gravity well, the more extreme the effects became. Gravitational time dilation was reaching its extreme. But what exactly happens to time at the event horizon? To answer this question, we need to dive deeper into the mathematics of general relativity. Near the event horizon, the space-time curvature becomes so intense that the differential rate of time, how fast time flows, reaches zero from the perspective of a distant observer. This doesn't mean that time has literally stopped for someone falling into the black hole. From their perspective, time would continue to pass normally. However, for an external observer, it would appear as though the person falling in had been frozen in place, forever suspended in the last moment before crossing the event horizon. This paradoxical nature of time, flowing normally for one observer while appearing frozen for another, arises from the relativity of simultaneity. Einstein showed that the concept of now is not absolute, but depends on the observer's frame of reference. In the extreme environment, such as near a black hole, this relativity becomes starkly apparent. As an object continues to fall into a black hole, the story of time takes on even more bizarre twists. From the perspective of a distant observer, the infalling object appears to slow down asymptotically, approaching the event horizon without ever actually crossing it. This phenomenon is tied directly to the immense gravitational field, which distorts space-time in such a way that light emitted from the object is stretched into longer wavelengths, a process known as gravitational redshift. Eventually, the object becomes invisible as the light is redshifted beyond detection. But what happens from the viewpoint of the object itself? For someone falling in, the event horizon marks no special boundary. They would cross it without noticing anything unusual at that precise moment, and time would seem to flow normally. However, as they approach the singularity, the core of the black hole where space-time curvature becomes infinite, space and time themselves become so warped that the very concepts of direction and time cease to have conventional meanings. The equations of general relativity break down here, and quantum mechanics must be invoked to describe the fundamental structure of space-time. But if the object seems to disappear from the universe, what happens to all the information it contained, its mass, energy, and every detail about its existence? Does this information simply vanish, defying the laws of physics, or could it be preserved in a way we can't easily perceive? This brings us to the holographic principle, a concept that has emerged from the study of black holes and quantum gravity. The principle traces its roots to the groundbreaking work of Dutch theoretical physicist Gerard Hooft and its later development by Leonard Susskind. Both were grappling with a central problem in black hole physics, the black hole information paradox. Gerard Hooft, already a prominent physicist in the 1980s, had spent much of his career thinking about the relationship between quantum mechanics and gravity. As a scientist deeply influenced by the work of Stephen Hawking, Hooft was fascinated by the realization that black holes radiate energy, a process now known as Hawking radiation. According to Hawking's calculations, this radiation causes a black hole to lose mass and eventually evaporate. But there was a catch. If black holes eventually disappear, where does the information contained within them go? This presented a crisis in physics. According to quantum theory, information about a physical system is never truly lost, but Hawking's work seemed to suggest that when a black hole evaporated, all the information about the matter it had swallowed would be irretrievably erased. This violation of the principles of quantum mechanics led to the so-called information paradox. Hooft's thought process was shaped by this paradox. He knew that either quantum mechanics or general relativity, or both, had to be incomplete. One day, while contemplating the event horizon of a black hole, he had a key insight. What if the information about everything that falls into a black hole doesn't get lost, but is somehow stored at the horizon itself? This would mean that the event horizon acts like a two-dimensional surface, capable of encoding the three-dimensional information of everything that enters the black hole. This line of thinking, though speculative, resonated with the strange mathematics of black holes. Hooft began to suspect that the entire universe might operate similarly, where the information of all physical processes could be encoded on a distant boundary, just like the event horizon of a black hole. It was Leonard Susskind, an American physicist known for his work in string theory, who would later expand on Hooft's idea. Susskind had been troubled by the same paradox and saw Hooft's concept as the key to resolving it. Building on these ideas, he developed the holographic principle, which posits that all the information within a volume of space can be represented on the surface, enclosing that volume. This was a radical rethinking of how space and time might work at the deepest levels of reality. His analogy was simple. Think of a hologram. A hologram is a two-dimensional surface, yet it creates a three-dimensional image. What if, in a similar way, the three-dimensional universe we experience is actually a projection from a two-dimensional surface? In terms of time, this suggests that what we perceive as the flow of time might be an intricate projection of deeper, lower-dimensional processes, much like how the three-dimensional world we experience could be a holographic image emerging from a more fundamental two-dimensional reality. This possibility opens the door to rethinking time not as something that moves from past to future, but as an ever-present structure where all moments coexist simultaneously. Some suggest that past, present, and future could all exist together in a kind of unchanging, eternal framework. Picture the loaf sitting on your kitchen counter. Each slice represents a particular moment in time, a specific event or experience in your life. The slice where you are now, sitting and viewing these videos, is what you refer to as the present. But crucially, the other slices are all there too. The day you were born, your first day of school, that time you aced a test, your first love, and perhaps even the moment of your final breath. None of these slices disappear or get erased once they've been experienced, nor do they need to be created as you move forward through time. They already exist, side by side, within the loaf. Now let's take this a step further. Imagine that instead of a single loaf, there's a bakery full of loaves, with each loaf representing the life of a different individual or the history of a different object, from the motion of distant galaxies to the decay of subatomic particles. These loaves don't exist in isolation, but are connected, influencing one another. Some slices in your loaf might overlap with slices in other loaves, the moment you meet someone for the first time, for example, or when a historical event occurs that affects millions. These intersections are moments where different threads of the universe weave together. This idea is widely known as a block universe. In this model of reality, the past, present, and future all coexist, fixed within a four-dimensional space-time block. Time is not something that flows from moment to moment as we typically experience it. Instead, all moments exist simultaneously, like pages in a book where the narrative is already written from beginning to end. This notion fundamentally challenges our everyday perception of time as a sequence of events unfolding. But how did we arrive at such a strange and often unsettling idea? Over the following century, many physicists expanded on this concept. Carlo Rovelli, a theoretical physicist known for his work in quantum gravity, is one such scientist. Rovelli proposes a relational view of time, suggesting that what we call time is simply a measure of change between different configurations of matter in the universe. From this perspective, the idea of an objective present moment doesn't make sense. Instead, all moments are equally real, existing in a relational web within the block universe framework. This deterministic view, where the future is already laid out, just as the past is, has deep implications for how we understand free will and the nature of reality itself. If time is a dimension in space-time, then what we perceive as choice may simply be our journey through an already determined path in the block. In more recent work, physicists like Sean Carroll have extended discussions of the block universe into the realm of quantum mechanics and cosmology. From the perspective of someone within the block, time appears to flow, events seem to unfold, and choices seem to matter. But at a deeper level, all these moments, births and deaths, choices and chances, are simply coordinates in space-time, all existing simultaneously. But this isn't the end of the story. Let's take this idea even further. What if the loaf itself is an illusion? What if there is no before or after? Not because all moments exist at once, but because the very concept of moments, of any sequence, any progression, doesn't exist at all. What if everything we think of as reality, every event, every memory, every tick of the clock, isn't just coexisting, but is, at its core, nothing? A self-described outsider to the academic establishment, Julian Barber never pursued the traditional path of tenure or professorship. Instead, he worked as a translator to fund his inquiries, moving from one project to another, piecing together his theory bit by bit. He was an anomaly, a physicist without a university affiliation, working from his home in the Oxfordshire countryside. Barber's academic background, however, was solid. His early education placed him at the intersection of the two fields, mathematics and physics, that would underpin his later work on time. But even with these credentials, Barber chose to follow an unconventional path. In his early career, Barber had deep doubts about the nature of time as presented by contemporary physics. His first doubts about the nature of time emerged from his studies of general relativity and quantum mechanics. In the 1960s, while working on his PhD dissertation at the University of Cologne, Barber became captivated by Einstein's theory of general relativity, which treats time as part of a unified fabric called space-time. In this framework, time does not flow in the way we experience it. Rather, it is a coordinate, no more special than the three spatial dimensions. Events exist within the space-time fabric like dots on a map, simultaneously present without any one event inherently becoming another. But if time did not flow in general relativity, Barber wondered what was its real nature. Around the same time, he became intrigued by quantum mechanics, a field where time plays a peculiar role. In Schrödinger's equation, time is simply a parameter, and quantum states evolve deterministically. Yet when we observe a quantum system, we experience seemingly random, discrete outcomes, suggesting a disconnect between the deterministic equations and the probabilistic reality we encounter. These inconsistencies between quantum theory and relativity planted the first seeds of doubt in Barber's mind. What if the problem wasn't with the theories themselves, but with how they used time? Barber's quest for answers led him to explore an obscure idea proposed by the physicist John Wheeler, that the universe might be described in terms of configurations rather than evolving states. Wheeler had suggested that instead of tracking the changes a system undergoes over time, physics could focus on the possible arrangements of matter in space, what Barber would later call the nows of Platonia. This was one of the key moments in Barber's process, was recognizing how memory plays a role in our perception of time. He realized that the sense of flow, the feeling that the present arises from the past and flows into the future, might be an illusion generated by how information is stored. In certain nows, records of past configurations are encoded, giving us the impression that events have unfolded in sequence. However, Barber argued, these memories are just features of individual configurations, not evidence of an actual passage of time. The arrow of time, our perception that the past lies behind us and the future ahead, emerges from the way information is structured within specific configurations, not from any fundamental property of the universe. In 1999, Barber published his monumental work, The End of Time, a book that crystallized his ideas and brought them to a broader audience. In it, he laid out his discovery that time is not a fundamental aspect of reality, but an emergent illusion. Platonia is the conceptual landscape at the heart of Julian Barber's findings, named after the ancient Greek philosopher Plato as a homage to his theory of forms, the idea representing the collection of all possible configurations of the universe, each a distinct, timeless now. In Platonia, these configurations exist independently of one another without any intrinsic order or sequence. Instead of a continuous, flowing timeline, reality is composed of a vast, multi-dimensional space where every moment exists simultaneously, complete in itself. There is no past or future, only a static array of possible states, each representing the entire universe at a given instant. Mathematically, Platonia is analogous to a configuration space, a structure used in physics to describe all possible states of a system. A helpful way to imagine Platonia is to think of a shuffled deck of cards spread out on a table. Each card shows a unique arrangement of symbols like spades or diamonds, just as each point in Platonia represents a distinct configuration of the universe. The cards do not follow a specific order unless we impose one. Similarly, in Platonia, there is no inherent progression from one configuration to another. Time, as we experience it, arises only when we mentally arrange some subset of these states into a meaningful sequence. One of Platonia's key strengths lies in its ability to address the arrow of time problem, the mystery of why time seems to move only in one direction. In traditional physics, the equations governing fundamental processes like the motion of particles are time-symmetric. They work equally well whether time moves forward or backward. Yet, in the macroscopic world, we observe irreversible processes, such as a glass shattering, but never reassembling. Barber's Platonia offers a different solution. The arrow of time is not fundamental, but rather an emergent property. It exists only in regions of Platonia where configurations increase in complexity, such as the evolution of our universe. We perceive time's direction because the configurations we experience happen to contain increasing patterns of structure and order. Barber's Platonia shifts the focus from evolution through time to the geometry of configurations. He suggests that the laws of physics may be understood better as constraints on the shape of this space of possibilities, rather than as rules governing temporal change. For example, general relativity could be reinterpreted not as describing how space-time evolves, but rather as defining the relationships between different states in Platonia. In this way, the geometry of Platonia becomes the fundamental fabric of reality, with time emerging only as an illusion, a byproduct of the paths we imagine through this space. Julian Barber's work on time as an illusion echoes the ancient tension between Chronos and Tempus, two distinct concepts of time. Chronos originates from Greek mythology, where it refers to time as a relentless, unfeeling force that governs the physical world. It is the kind of time that can be measured, seconds ticking away on a clock, days marked by the rising and setting of the sun. In physics, this idea of time underpins our understanding of motion, causality, and change. Equations from Newton's laws to Einstein's relativity rely on the notion of time as a parameter that flows forward, enabling events to unfold in sequence. Chronos is objective and consistent, providing a shared framework for organizing the world and tracking progress. However, Chronos is also indifferent. It does not care about how time is experienced by individuals. Whether you are bored or exhilarated, time measured by a clock passes uniformly. In this way, Chronos embodies the mechanical clockwork nature of the universe, where everything proceeds along a timeline, indifferent to human emotion or perception. In contrast, Tempus is subjective time, the time of human experience. It is fluid and malleable, stretching or contracting depending on mood, focus, and context. Think of how time seems to fly by when you are deeply engrossed in a conversation, or how it drags during moments of anxiety. Tempus is not concerned with precision or measurement, but with meaning. It reflects the way we interpret our experiences and weave them into narratives that give structure and significance to our lives. Tempus is also closely tied to memory and anticipation. Our understanding of the present moment is influenced by memories of the past and expectations of the future, creating a sense of continuity. In this way, Tempus allows us to feel connected to both where we've been and where we hope to go, forming the emotional underpinnings of stories, plans, and identities. Unlike Chronos, Tempus is personal and unique to each individual. Our experience of time is deeply subjective, shaped by the brain's complex processes and influenced by attention, memory, emotion, and physiology. Although we take it for granted that the present moment is unfolding seamlessly in real time, Psychological research shows that our perception of time is neither precise nor objective. In fact, every experience we have is already slightly in the past by the time we consciously register it. The brain's construction of temporal experience introduces subtle delays and distortions, meaning that what we perceive as now is a best-guess reconstruction of events that have already happened. The brain processes sensory input, touch, sight, sound at different speeds. Vision, for example, is relatively fast, while tactile sensations, such as touch, can take longer to be processed, and auditory signals are processed differently still. To create the illusion of a continuous present moment, the brain synchronizes inputs arriving at different times, stitching them into a coherent narrative. However, this process introduces a delay, often referred to as the perceptual lag. By the time you become aware that you've touched a surface, your hand has already been in contact with it for a few milliseconds. Experiments in neuroscience have demonstrated this time lag. One famous study conducted by Benjamin Libet in the 1980s investigated the relationship between brain activity and conscious awareness. In this experiment, participants were asked to press a button whenever they felt like it, while also noting the exact moment they made the conscious decision to act. Surprisingly, Libet found that brain activity associated with pressing the button, the readiness potential, began around 300 milliseconds before participants reported being aware of their intention to act. This suggests that decisions, or at least the processes leading to decisions, are initiated unconsciously, with our conscious mind becoming aware only after the fact. Other experiments have also explored the subjective nature of time perception. In a well-known phenomenon called temporal binding, the brain tends to compress the time between two related events, such as pressing a button and hearing a sound shortly afterward. This compression leads people to experience the cause and effect as occurring closer together in time than they actually did. Temporal binding reflects how the brain works to smooth out discrepancies, making events appear more synchronized than they really are, which supports the sense of a continuous flow of time. Moreover, the brain's clock isn't perfectly uniform. It can speed up or slow down, depending on various factors, such as attention, emotion, and physiological states. For example, when you are deeply focused on a task or in a state of flow, time seems to pass quickly. Conversely, during moments of boredom or fear, time appears to drag. In stressful situations like an accident or emergency, people often report that time seemed to slow down, giving them more room to react. Research suggests this experience occurs because the brain's amygdala, which is involved in emotional processing, becomes hyperactive, enhancing memory encoding and perception. As a result, these moments are remembered with greater detail, which tricks us into thinking they lasted longer. In addition to perceptual lag, the brain is limited by temporal resolution, which determines how finely it can slice up time. Neurophysiological studies indicate that the brain processes sensory input in chunks, each about 30–50 milliseconds long. This discrete processing imposes limits on how smoothly we experience time. For example, even though visual stimuli change continuously, the brain interprets them in these small intervals, somewhat like the frames of a movie. As a result, rapid changes, such as a bird flying by, are stitched into a seemingly continuous motion, though your brain is processing them in discrete steps. This imperfect synchronization can create interesting illusions. Consider the flash lag effect, a visual illusion where a moving object appears to be ahead of a flash that occurs at the same time. This illusion occurs because the brain compensates for delays in processing by predicting the motion of the moving object. By the time the flash is consciously registered, the brain has already updated its guess about where the object should be, causing the moving object to appear further along its path. One of the more everyday ways you can observe this delay in action is when you stub your toe. The tactile sensation of the impact may seem to coincide with the moment you feel pain, but the two signals, touch and pain, actually travel along different neural pathways at different speeds. By the time your brain assembles the sensations into a coherent experience, some time has already passed since the actual moment of impact. You are, in effect, always experiencing the world slightly behind real time, though your brain masks this lag by aligning sensations as closely as possible. The combination of these effects, perceptual lag, temporal binding, emotional modulation, and discrete neural processing, means that our experience of time is far from the objective flow we often assume. Time, as we perceive it, is a psychological construction, shaped by how the brain integrates sensory inputs, manages memory, and predicts future events. This suggests that the present moment is an illusion, a kind of guesswork the brain performs to keep our experiences feeling coherent, despite the underlying delays and inconsistencies. If time as we feel it, stretching, compressing, slipping away unnoticed, or dragging endlessly, is an illusion shaped by our brain's imperfect processing. And if even time as described by physics, measured in seconds, flowing from past to future, is merely a mathematical tool rather than a fundamental reality, then what is time, really? If clocks, calendars, and timelines are just constructs we impose on the universe, does time exist independently at all, or is it simply a convenient fiction? Can we trust the feeling of now if our conscious awareness is always slightly behind reality? If the flow of time is not intrinsic to the universe, but a product of human perception and narrative, what does that say about causality, memory, and the very idea of change? And if time is merely a sequence of static moments, as Julian Barber suggests, each existing independently in a timeless state, so what is time? Time doesn't move the way we think. Every moment in time is already out there. We feel like time is moving because we are only able to experience one moment at a time. But in reality, all the moments are fixed and unchanging. It's like we are stuck in a single frame, unable to see the bigger picture. In this theory, the universe isn't a place where things happen over time. It's a place where time itself is a part of the structure. Everything is locked into a four-dimensional block. Past, present, future, all fixed in place. Your entire life from birth to death already exist in the structure, but they are all out there, unchanging. But what if everything is already written? Looking to the future, it's conceivable that scientists will uncover new insights that shed light on the true nature of time. With advancements in technology and theoretical physics, we may eventually develop a framework that clarifies its essence, whether it exists independently, is a dimensional aspect of the universe, or something entirely different. Until then, the ambiguity surrounding time is a reminder of the limits of our current understanding. Rather than being caught up in the debate about time's essence, we might find more meaning in cherishing the time we have, whether time is real or an illusion. It's central to the human experience, shaping our relationships, actions, and identities by focusing on the present, on what we can control. We can live fulfilling lives regardless of whether time exists, as we think it does.